Hello. So continuing our discussions on robotic tactile sensing. Previously, we showed that comparing with the human skin, we can develop something called an e-skin, an electronic skin, and it is based upon something called uh, bionic corpuscle, and it mimics what is known as the Meissner corpuscle in the actual human skin. Now, this Meissner corpuscle it consists of a dermis, an epidermis, a dermis, and in between there is a deforming layer. Now, usually in the bionic system, this deforming layer is made up of an Ecoflex gel, which is very soft gel, and this is how the pressure distribution. This actually creates the stress field, which gets sensed by the tactile receptors. Now, we do have, apart from the Ecoflex, the whole bionic system, the construction of the whole binary system, if you go into the details, it consists of five functional layers. Five functional layers. The first one is known as PDMS. PDMS stands for polydimethyl siloxane. Polydimethyl siloxane. The second layer is the copper or polyimide serpentine electrode. Serpentine electrode. The third layer is the pressure sensor array. And the fourth layer is the Ecoflex gel. The fourth layer is the protective silicone layer, and it actually it corresponds to the connective tissues that we have in the actual human skin. So it is analogous to the connective tissues, which are responsible for the stability of the whole system. So as connective tissues, tightly bound connective tissues provide stability to the actual human skin septum system. Similarly, here we have protective silicone layers, and at last we have that lower copper on polyimide serpentine electrode. So pictorially it looks something like this. You have the first layer is your PDMS, which will be followed by the first laminated or the island bridge alliance system, copper pi electrode system. Secondly, we have the TPU called carbon black layer. So this actually forms the sensor array. This is followed by the deformation gel, the eco gel. This is the EcoFlex gel, or the layer which is responsible for taking the deforming and creating the pressure distribution. Then we have this silicon layer for production. This is how the whole system stands, the bionic corpuscle stands. Now, this now this tissue wrapping system, as found in the case of Meissner corpuscle. In Meissner corpuscle, we have this tissue wrapping. And similarly, as we have previously stated, it is analogous to the silicon structure we have in the case of a bionic system. Now, to detect the three-dimensional force, we do have a three-dimensional force which is getting detected, and it is being converted into a stress field. Similarly, the same concept has been inculcated into this bionic capsule, and it is based upon a simulation where the force is being applied not at 90 degrees but at an angle 45 degrees. Now, the idea is to determine the displacement vector. So the displacement vector is actually the one which determines how much pressure distribution has taken place. Now, when we have this 45-degree angle force applied to the deformation layer, the pressure distribution at the top surface, distribution at the top surface is almost constant. Is constant, whereas in the bottom of the surface, it actually moves with the direction of the shear stress. The whole idea of keeping it at 45 degrees is to make sure that we do have some sort of shear stress acting. So at the top surface, which is in contact with the external force, the pressure distribution is almost constant, whereas just below it, the bottom surface, the pressure distribution, it varies. And at the horizontal contact point, the horizontal displacement is relatively stationary. So also the horizontal displacement at the point of contact is stationary, and it moves as we go down with respect to the top surface. So the displacement vector here, which is actually causes a displacement due to the shear stress, this is actually an indication of the shear field, stress field in the 3D force. Now, to quantify how much pressure distribution is there, we need to have some quantification factors. First one is your center of gravity of the deformation layer, and it is given as the first one is equal to summation of I and j xi fij divided by I fj fij, and this is for the x. And for the y it is again I j yj fij divided by fij fij. So here xi and xj, xi and yj, they are the sensor location, locations of the corresponding layer, and fij is actually the magnitude of the pressure. So it defines the center of gravity of the deformation layer. And similarly, we can actually also find out the hardness sensation. And hardness sensation is based upon the diffusion length. I mean, the distance between the pixel and the center of gravity. This is given by dij, and based upon the pressure that has been provided, we can have something called a diffusion length, which is equal to again summation j dij fij divided by summation j fij. Fij again is the pressure applied, and dij is the pixel to center of gravity difference. Now, the idea of this diffusion length is based upon the fact that if this biomimetic receptors are pressed at the same speed until a certain pressure is reached. So they are being pressed at a certain speed, and to reach a certain amount of fixed pressure, let's say it is 5 newtons. So as the harder material, the relative deformation of indentate becomes smaller, and the pressure distribution is more concentrated. As the hardness increase, so deformation of the place where the pressure has been applied, it is called the indentation, deformation of the indenter. The indent has been made, it becomes smaller, and the pressure distribution is also concentrated. So we are actually by hardness sensitivity, we are actually focusing on this pressure distribution. Okay, so based upon this diffusion parameter, this diffusion length, we can this diffusion length, we can clearly find out where has the pressure distribution. So this is indication of the pressure distribution. The hotter it is the material, the lower will be the pressure distribution. Okay. And so with the help of this electronic skin, we can find the hardness, or we can actually see whether a material, a comparative hardness, not qualitatively, but not quantitatively, but comparatively, we can detect where has been the hardness high and whether there is low, and we can also determine the stress field by the center of gravity as indicated.